Hello from London. I'm Johan. I'm Swedish, but I currently live and work in the UK. I'm a maintainer of various open source projects, including the gRPC-Gateway and Improbable's gRPC Web. I've contributed to the Go standard library, and I run a blog writing mainly about Go and gRPC. I work at Buff, where we think about Protobuf, so you don't have to. This is my first Go West, and it's great to be part of this conference. I'm here today to talk about HTTP/JSON and gRPC. Today, we're going to look at what HTTP/JSON is, what it's used for, and explore some of the problems associated with it. We're then going to go a little into Protobuf and gRPC before learning about how we can get the best of both worlds with the gRPC Gateway. We'll then have some live demo of it in action. What do we mean when we say HTTP/JSON? We mean a RESTful interface making use of the HTTP verbs get, post, put, patch, delete, and JSON as the payload content type. This is the de facto standard for most public APIs today. Sometimes it's not entirely RESTful, but it's almost always using JSON. It's easy for humans to read and write, it's got native JavaScript support, all is well, right? Is everything well? As anyone who's ever had to quickly push a configuration fix to your JSON configured service knows, trailing commas are forbidden in JSON. I wish I was joking in saying that this is a big problem, but entirely new formats have been developed to deal with this. There's also no support for comments. It's unnecessarily verbose on the wire, but compression can help mitigate this. In large deployments, the marshalling and unmarshalling of JSON is a constant strain on response latency. Most importantly, it's not well typed enough, and there's no single way to define the interface types. OpenAPI is an option, but it's not globally adopted. Most of these problems stem from the fact that JSON was designed to be human-readable, but also effective for a machine to use. These two properties are, unfortunately, incompatible. Fortunately, though, there is a better option. Protocol buffers have recently become more and more popular for use with internal APIs, and for good reason. They provide an efficient wire encoding, cheap marshalling, good type support, and a single source of truth for your API description. Generators use the Protobuf definitions to produce language-specific code. Projects such as Twerp are basically the traditional HTTP/JSON application with the JSON part replaced with Protobuf. This snippet here is an example of what a very simple profile might look like. We define the type user and a single field, ID, of type string. We're going to be using it with gRPC. gRPC is an RPC framework developed to make RPC as fast and safe as possible. It uses HTTP/2 by default to efficiently and quickly send the data between client and server, removing most of the overhead of HTTP/1.1. It uses Protobuf as the default transport encoding, piggybacking on it for type safety and speedy marshalling. It is possible to use JSON with gRPC if you really want to, but it's kind of pointless. It maps the service definitions in a Protofile API to services in the generated files. As we can see in this example here, we've added some extra messages for inputs, and we've defined a new service with two methods. Given this, we can generate everything we need to allow the use of gRPC between the client and server. Note that list users streams the results of the operation to the client, something which is not trivial to accomplish with HTTP/JSON. But if you were already able to use gRPC, you wouldn't be listening to this talk. Unfortunately, it's not always so easy to switch entire application stacks to a new framework. Often there are a number of reasons why we keep using old standards when new, better alternatives are available, such as compatibility with existing systems, management pressure, and, in this case, the still prevalent expectation that a public API should be using HTTP/JSON. What can we do when we want to use gRPC, but are forced to use HTTP/JSON. This is where the gRPC-Gateway comes in. The gRPC-Gateway project allows you to design gRPC and HTTP/JSON services at the same time. It uses a custom Protobuf generator that generates a simple reverse proxy that translates on the fly from JSON to Protobuf and back again. It allows you to define a URL path and a HTTP verb to gRPC service method mapping with a simple annotation scheme in the protofiles. It also provides a Swagger/OpenAPI generator in case you have some generator you want to use that requires the OpenAPI format. It has been widely adopted within the gRPC community wherever a HTTP/JSON interface is required. In this example, I've taken the previous example and added the HTTP/JSON annotations. As you can see, the HTTP verb and URL path mappings are defined within the RPC definitions. How does it work? This image here shows the basic building blocks of the gateway. You generate a gRPC service as usual with ProductGen-Go, and then you use our custom generator, ProductGen-gRPC-Gateway, to generate a gateway handler file which registers the mapped HTTP verbs and URL paths to a central MUX, which is then used to serve the external HTTP/JSON interface. It is common to serve the gateway and gRPC server on different ports on the same server to allow both HTTP/JSON clients and the gRPC clients, but this is not mandatory. The gateway can also be used with non-Go gRPC services. Let's take a look at an example. I'm going to show you an example of the gRPC gateway from my boilerplate repo. If you have a laptop at hand, please feel free to clone the repo and follow along. So now we jump into my gRPC gateway boilerplate repo, and the first thing we see here is the example.proto file. This is the proto file definitions that is used to generate the gateway. Now, as you can see, this is a typical proto file, so we have some imports here, we have a package declaration, we have a syntax declaration, and then we have the Go package option, which is important when you're writing or generating Go files from your proto file. And if we continue downwards a little bit in this file, we can see that we've got some Swagger annotations here, which are purely there to add to the Swagger file that we generate, or the OpenAPI file that we generate using the OpenAPI generator. So for example, you can add a version, some metadata links here, and there are other annotations that you can add in this space as well. And if we come down a little bit here, this will look quite similar to what we saw before on a previous slide. We have a service called user service, and we have an RPC here called add user. And the add user takes an add user request and returns a user type. And then we have the HTTP mapping down here. So as you can see, what we're saying here is that we want /API/v1/users to map to this gRPC method. And we're also saying that the body of the JSON document that we expect on that URL is going to be the equivalent of the JSON representation of the add user request. So if we jump down a little bit here, we can see that the add user request is actually just an empty request. It doesn't have any information at this point because the API is designed so that you don't need any information to add a user. And we can see that we have some more metadata here. This is purely for the Swagger generation. It doesn't affect the Go server generation at all. We also have list users here, which is a list method. And this one is a little bit interesting because it returns a stream of users. Now we'll see an example of exactly how that works in HTTP, but for gRPC that's quite natural. And as you can see, in this case, a list method would normally be something like API/v1/users, and it's using the get verb. And then again, we have some metadata down here, and the list users request is completely empty. And the user message is just a simple ID. So let's look at exactly what we do to implement this. Then we can open the server file. Now this backend struct here is what will implement the implementation of our servers. So we have a mutex and we have just a slice of users. In this case, we've already generated all of the types, so we don't need to worry about generating things right now. And then, as you can guess, when we add a user, we lock the mutex, we create a user with a random UID, we just append that to our internal slice, and then we return the user that we just created. And for list users, obviously, we do a read lock, we loop over all the users, and then we send them out on the server. So that's both add user and list user already implemented. Now let's take a quick look at what the main function looks like. If you're familiar with gRPC, then this is going to look quite familiar to you already. So you can see we're creating just a logger here to get some information from the gRPC server. And then we say that we want to serve on port 10,000 on the interface 0000. So that's just, kind of like localhost. We want to serve get a TCP listener, and then here we're creating a gRPC server, and in this case we're setting it up with some credentials using a locally generated certificate and key. Obviously you're going to want to generate your own ones or use some sort of certificate management system for your own server. This is just here because I would like to show the server running with HTTPS or TLS instead of turning off encryption altogether. And then we register user service server to the generated, this is a generated method based on the, the example proto service. And this takes a PB example user service server. So if we jump into that quickly to understand what that means, we can see that this is actually the interface that was generated from the proto file. So we have the add user, list users, and if we jump back here, you can see add user, list users, and this corresponds to the definitions that we had. So basically this interface has to be implemented by anything that you want to serve on the gRPC server, and server.new does that. This server.new is what returns exactly what we were looking at in a minute ago. And then we just serve that. And then what the gRPC gateway part, if we jump into that for a second, after we've started the gRPC server on the local machine, then the gRPC gateway simply dials the gRPC server that we just started, using the same transport credentials, of course, to make sure that it trusts the server certificate. And we use with block here to make sure that we finish dialing before we continue setting up the gateway. And now the gateway can create a server mux, register, and this is another generated method based on the gRPC gateway generator. So in this case, you register user service handler, and it takes a gRPC client con and the gateway mux that we just created here. And then what you have to do is create another HTTP server, and then just simply use the gateway mux.serve HTTP to serve the website, serve the gRPC gateway. And what we're doing here is a little bit extra, which is that we want to, when we get a request for the path API, we want to serve the gateway. But if we don't, then we want to serve our open API handler. And I'll show you quickly what that means, what it looks like rather, because this is just a little bit of extra flair to show what happens when you can use the open API. So let's run main. Okay, that's serving. It's serving the gRPC gateway and OpenAPI documentation on 00011,000. So let's switch to my Firefox tab. Just reload that page quickly. Okay, so here you can see this is entirely generated from the document that we just saw, the proto file. And so we have the get request here, list users, and a post request here to add a user. We can try running list users now, and obviously we haven't added any users, so we expect this to return absolutely nothing. And indeed, content length 0, pretty telling, no users added. So if we go ahead and add a user first, and you can see this is the JSON body that we were talking about. We have a completely empty body because the add user request takes no parameters. So let's execute that and see, okay, we created a user. This is the ID of that user. And if we then go to list users, we can see that we have gotten that user. And the reason that we wrapped in this result envelope is because we are actually streaming the results back using HTTP chunked encoding. And you can see that this is the entire struct that you would expect. The result wraps the kind of successful message, and we also have an error field here, which is optional. If there is an error during the handling of a stream, you need to be able to say that in the middle of the message rather than, you know, returning a completely different type. So this is the entire envelope, and most of the time you can just expect the results to be populated, and the error will only be set if there was an error. Okay, now let's see what happens if we want to add a field. Let's quickly go to example proto, and let's say we want to add a name to the user. Then obviously when we do an add user request, we will have to take a string name. And that's all we do. We don't need to do anything else here. If we run make generate now, that's going to regenerate the files. We can then jump into server, and we'll have to save the request at this point. But as you can see now, we have a name here, and we simply add the name when we create a user, and that should be it, really. Let's try and run that now. And let's jump back into Firefox. Just gonna reload this page, see if, yeah, no, we're gonna need to just turn off the cache. When we reload, now the body requests a name. Let's create this user called Johan. Okay, created a user with the name Johan, and if we run list users now, indeed, the user has been persisted to our backend and can be served on subsequent requests. It's pretty cool. Let's explore some of the specific features of the gateway, starting with the well-known types. These types are part of what you might call a Protobuf standard library and are always included with the Proto-C compiler, meaning you don't have to manually manage their downloading and generation. They use a special namespace, google.protobuf, which makes them easy to recognize. These types are predefined messages and include messages for handling timestamps, durations, wrappers of primitive types, and others. All of these types have special cases built into them for the gateway. So whenever, for example, you need a timestamp, make use of the well-known type. As you can see here, I've added some examples. The timestamp type marshals to and from an RFC3339 timestamp string. The uint32 value can be used to have nullable uint32s, and the struct type can be used to store arbitrary JSON structures. Please use the last one carefully, as the Protobuf representation is a mess to work with and should only be a last resort. Let's take a look at what that looks like in action. Now I've jumped to a different branch here, where we also have the getUser method on the server. But let's take a quick look at the proto file again. Now you can see that we have addUser here, and we also have getUser, which maps to the API v1 users with an ID as a parameter, as a path parameter. So the getUser request, which takes a ID only, reads the ID directly from the path using this path expansion. Now if we look at the addUser request, we've added the google.protobuf struct type here, so that you can give arbitrary JSON metadata in the create request, and the user now contains both a create time and the metadata that was used on creation. So if we run the server again, okay, we have now getUser by ID. So let's try and add a user here, and let's put an email there, and then in the metadata we can put literally any kind of structures that we want. Let's say we add the pet dog here, and then we send that on its merry way. Okay, and then you can see the create time was now populated, and it's mapped to a RFC3339 string, and the metadata was preserved as well. Another well-known type has a special use in the gateway. Most Protobuf primitive fields, such as strings and integers, are non-nullable, so in order to do partial updates, the best practice is the use of a special message type called field mask. Exposing this implementation detail to your users, however, is pretty nasty, so the gRPC Gateway supports translating JSON fields to a field mask and resource type. Fields that are found in the input JSON are used to populate the resource and field mask automatically. This code here shows an example structure with the service omitted. The output only comment indicates that the field is not mutable via partial updates, which is in line with the Google API Design Docs recommendations. This support was entirely the result of an open source contribution from Roman Azami and Daniel MacDonald. Let's take a look at an example of this in use. And now, as you can see, I've added a new method here called updateUser. And the updateUser takes a patch verb, and the body of that request is the user type, which is interesting because the updateUser request actually contains both a user and an update mask. Now, this is how the Google API design documentation recommends you format your update API if you're using a field mask. So what the gRPC Gateway now does automatically is, just based on the input blob, it will populate the field mask and the user based on the input. So let's take a look at what that looks like in the server implementation. If we go to update users here, we can see that it first gets the ID of the user that we want to update. And if it can't find it, then it returns an error saying, we couldn't find the user that you wanted to update. And then if we go through here, you can see that it will switch on the path in the update mask. So the only field that we actually allow you to update is the email. And if it finds the email path being set, then it will set the user's email, the stored user email, to u.email. And returns the updated user as well. So let's see what that looks like if we run it. Now, as you can see, we have the patch here, which updates the user. So let's first try and create a user. Let's not use any metadata this time because it's just really messy. So we create the Johan user, and it has the ID, this ID. And then what if we made a mistake and we need to change that user's email? Then we can use the ID that we were using there, and we can try and update it directly here. Actually, my email is now johan2@foo.com. And as you can see, in the body, we only need to specify the user properties themselves. We don't have any update mask or anything here. We just say email equals blah. And indeed, because the proto schema that we were looking at decided that the user ID is part of the path, it's even a separate part. So now we can do that, and we run execute, and indeed it's returned the updated user. And we can try and just list users to see if that persisted itself. If we persist users, then we can see that Johan2 has indeed been saved. So that patch request worked really well. So how do we handle errors in our service? When working with gRPC, we use the status type for errors, which includes a message and a code. The gRPC Gateway automatically translates the codes into appropriate HTTP status codes according to the google.rpc.code definitions, which you can see an example of here. If you have more specific needs for your error handling, such as a custom error struct format, you can create your own error handling function and configure the runtime mux with it on startup. Here we have an example of an error handler that sets the response code to one that is mapped from the gRPC status and the response body to simply be the error message. Note that using custom errors like this will break the default OpenAPI generator definitions. So let's see what this looks like. Now you can see I've jumped into the error handling branch, and it won't have changed much here, these functions all look the same still, but if we scroll down a little bit, we can see now that we have a custom error handler function definition down here. And this is exactly the one that was in the example before. We get the HTTP status from this convenient gRPC gateway code to HTTP status conversion, and then we just write that to the response writer. And then we can write the message itself straight to the response writer. So this is not going to be JSON at all. It's just going to be the message that we get from the error handler. So in this case, for example, instead of wrapping this in JSON, we're just going to see user ID with Q could not be found. So let's try that if we run that. Let's switch back to Firefox. Now, as you can see, this is looking just like the one before, but let's try and update a user that doesn't exist. Now, this is going to return an error because the server doesn't have this user. And as you can see, the response body is actually exactly the message that we had written there. It doesn't even wrap it in JSON. So this is kind of a bad use case for a custom error handler, but you could do anything you want in that error handler. And the way that let's jump back into the code quickly to just see how we wrap that up. Runtime.newServMux is called with runtime.withErrorHandler, and this uses the server.customErrorHandler. So that's where the custom error handler function comes in. You can obviously define that at any place of your application if you want to, but we've defined it together with the server. Let's jump back to the slides. So wrapping up, we've created a HTTP/JSON service, but used gRPC and Protobuf under the hood. This allows us to get all the benefits of the Protobuf IDL while still exposing the JSON interface externally. We've also managed to sneak a gRPC service into our stack, and now it's much easier to argue that gRPC might be something worth trying. New clients can use gRPC, and old clients can keep using the JSON interface. Most importantly though, we found an easy, robust way to write RESTful Go services, and we've only explored a snapshot of all that the gRPC gateway has to offer. Other features include the ability to set cookies, perform header-based authentication in interceptors, which is analogous to HTTP middleware, and much more. I hope you will, as I do, use the gRPC gateway for your next HTTP/JSON service. Thank you.